Hi, I'm Alessio Netti from the Leibniz Supercomputing Center in Munich, Germany, and I will be presenting our work for HPDC 2020, which is titled DCDB Wintermute Enabling Online and Holistic Operational Data Analytics on HPC Systems. As most of us know, HPC systems are becoming more and more complex as we approach the exascale era, both because of their scale as well as the intricacy of the new architectures that are being employed. In turn, several challenges in terms of energy efficiency, resiliency, as well as manageability of the new platforms are starting to arise. However, many HPC sites are starting to employ more consistently monitoring of system operations. Monitoring consists in the collection of sensor data from hardware or software components in the HPC system that can be leveraged to improve system operations. Processes of this kind go under the name of Operational Data Analytics, or ODA, which consists in deriving knowledge from monitoring data in order to improve system operations and enable proactive control loops. However, while monitoring is an established reality at most HPC sites, ODA is not, and the main reason for this lies in the severe lack of clear requirements as well as frameworks that would enable the adoption of ODA techniques in production HPC environments. However, the ODA research field thrives with models able to optimize and analyze most of the aspects of an HPC system's operation. On the right, we propose a taxonomy of the main ODA techniques that we identified in the literature. Among these, we have, for example, fault detection, which consists in distinguishing anomalous or catastrophic states within HPC components, enabling prevention or mitigation actions. Scheduling and allocation, on the other hand, consists in characterizing the performance and the behavior of HPC components, usually compute nodes, in order to make more informed and effective scheduling and allocation decisions. All of the classes that we show here on the right, in general, operate in very diverse ways, both in terms of the data sources that they use, as well as their modes of operation. As data sources, we find in-band data sources, which are produced within one component of the HPC system, say a compute node, and consumed within that same component by the ODA processes. We then find out-of-band data sources. These are produced within one component, are then sent out to a third-party server, and there the ODA process takes place. In terms of mode of operation, we find instead online operation, which is cyclical and periodical and produces an output resembling a time series. We then find on-demand operation, which is instead invoked at irregular time intervals, for example at scheduling time. From our taxonomy, we were able to derive a series of requirements that any ODA framework for HPC should respect. First, we find holism. Holism consists in the ability to expose a generic and global view of the HPC system's space of sensors. Secondly, we find flexibility, which is the support for all of the modes of operation that we discussed before, mainly online and on-demand. Then we have scalability. The framework should allow to instantiate ODA models with up to thousands of inputs and also at very fine timescales. At the same time, however, the overhead on running HPC applications should be minimal. Finally, we find abstraction, which is the support for constructs to simplify the instantiation of ODA models at a large scale, and modularity, which is instead a design based on simple interfaces to easily add in and out data sources and also maximize code reuse. To the best of our knowledge, there is currently no framework that satisfies all of the requirements that we discussed here. We tackled this research gap and we proposed the Wintermute Framework, which is our solution for operational data analytics in a generic, online, and holistic fashion on HPC systems. Wintermute is designed to be integrated into any monitoring framework. The main contributions of our work are the following. First of all, the requirements analysis for ODA that we just discussed. Secondly, the design of Wintermute, its integration within the DCDB monitoring system that will be described later, and finally the evaluation of Wintermute in several ODA use cases. We will start by describing the architecture of Wintermute. As said before, Wintermute is designed to be integrated into any monitoring system, and specifically it is designed to be encapsulated within the monitoring daemons that comprise the hierarchy of a monitoring system as a whole. Here, a monitoring daemon simply defines a process that is somehow part of the monitoring hierarchy, either by collecting sensor data or managing the sensor data collected by other daemons. Here, the Wintermute framework is integrated and isolated. In particular, within the framework, we find operator plugins. Operator plugins all comply to the same standard code interface and supply certain ODA capabilities, for example, classification, regression, or aggregation. Within operator plugins, a series of operators can be instantiated. Operators are the actual computational entities that perform the ODA processes asynchronously. Each operator works on a series of blocks. Blocks are containers of inputs and output sensors that respectively fuel the ODA analysis and are the product of the ODA analysis itself. The blocks are always associated to certain components in the HPC system, for example CPU cores or compute nodes. We will return on this concept later on in the presentation. We then find two additional components that have the task of connecting the Wintermute framework to the surrounding monitoring environment. These are the Query engine, which has the task of supplying to operator plugins the sensor data from the outside monitoring world through a uniform code interface, and the operator manager. The operator manager instead exposes the data produced by the operators to the outside monitoring system and also manages their life cycle. We implemented the architecture of Wintermute that we just described in C++11 and integrated it within the data center database. DCDB is the monitoring system that is developed at the Leibniz Supercomputing Center and that is also deployed on its HPC systems. Our implementation supports all of the ODA options that we described so far, and mainly online and on-demand modes of operation, the latter of which is supported by REST API, in-band and out-of-band deployment of ODA models, sequential or parallel operation of the models so as to tune performance according to the specific use case, and finally we also support the construction of operator pipelines to simplify complex ODA tasks. We will now briefly describe the architecture of the DCDB framework and how Wintermute is integrated within it. DCDB is inherently distributed and hierarchical in order to scale out to very large HPC installations. At the bottom of the hierarchy we find so-called pushers. Pushers are monitoring daemons which run within the components of the HPC system from which we want to collect sensor data. These have several monitoring plugins running which collect data from a series of data sources and then send it out via the MQTT protocol to a collect agent. A collect agent is a data broker which takes all of the data it receives via the MQTT protocol and forwards it to the storage backend. The storage backend is simply a persistent database which is currently implemented via the Apache Cassandra NoSQL data store. Wintermute is integrated both in the pushers and the collect agents. There is a difference in the two types of integration and in the options they provide to Wintermute plugins. Operator plugins deployed within pushers instantiate in-band use cases. Here, the operators have only access to the sensor data contained in the local cache, so in memory. This is extremely effective for in-band use cases because liveness of the data is guaranteed, as well as a very low overhead and, in general, optimal performance. In the collect agent, on the other hand, the Wintermute operator plugins can be deployed for the out-of-band use case. Here, the operators can access both data contained in the local sensor cache, which in the case of the collect agent contains all of the recent sensor data that passes through it, but can also query data from the remote Apache Cassandra data store. For this reason, this kind of deployment is suitable both for historical analysis of sensor data as well as system-wide analysis. We now describe the abstractions that we use in Wintermute to simplify the instantiation of ODA models at scale. First, a few words about the schema that we use in DCDB to describe sensors. Here, the keys are /separated strings like the one in the example. Here we have the LT sensor, which is simply a status indicator, belonging to compute node S02 in chassis 02 in rack 03. In other words, the last segment of the key is the name of the sensor. The preceding segments represent instead the components to which the sensor belongs in the hierarchy of the HPC system. This kind of representation is very similar to a file system path or also MQTT topics. Additionally, it can be leveraged to construct a so-called sensor tree. In the sensor tree, each inner node represents a component in the HPC system and thus a container of sensors. Leaves of the sensor tree instead are the sensors themselves. Here we show the path described in the sensor tree by the healthy sensor. We can now return on the concept of blocks in Wintermute. Blocks are containers of input and output sensors that drive the ODA computation. Blocks are always associated to a certain component in the HPC system, and this mapping supplies the name of the block. Additionally, a block always defines a subtree in the sensor tree. We will now explain how this is achieved. Here we present an example of a block constructed on the compute node S02. So the name of the block is rack03 chassis 02 S02. The block has the following input and output sensors. Starting from the inputs, we find the power sensor, which belongs to chassis 02 rack 03. So the power sensor of the chassis to which S02 belongs. Then we have the CPU cycles sensor of the CPUs that instead belong to the compute node S02, and similarly their cache misses sensors. Finally, as output sensor, we find the healthy sensor once again, which belongs to the compute node S02. We can now understand why a block defines a subtree in the sensor tree. Each of the sensors that belong to the block must be hierarchically related to the name of the block itself, in this case to the compute node S02. While it is possible to specify blocks explicitly as we just did, this is extremely inconvenient for large-scale ODA instantiations that involve thousands of compute nodes or CPU cores. For this reason, the Wintermute framework supplies a template-like language that allows to write very compact configurations that can then be reused thousands of times. Here we show an example of such a template. In this case, the input and output sensors are specified in a slightly different way. The names of the sensors are found as before. However, the preceding key segments, so the components to which the sensors belong, are not specified. In place of them, we find so-called sensor expressions, which are template expressions that restrict the set of nodes to which these sensors must belong in the sensor tree. They usually comprise two components, one specifying the vertical navigation in the tree, so at which level in the sensor tree should the sensor belong, and the second one specifying instead the horizontal navigation, so which nodes within the specified level should contain the sensors we are interested in. The template that we show here as an example can then be resolved as soon as we specify a name for the block. We will now explain the process in detail. Supposing that we want to instantiate the same block as before, the first required step is to define its name, which in this case is rack03 chassis 02 S02. We can then resolve the sensors. Starting from the output, we find the healthy sensor, which lies at the level bottom up -1. Bottom up -1 means that the sensor should be one level above the deepest level in the sensor tree. At this level, the only node in the tree which is hierarchically related to S02 is S02 itself. So we resolve the healthy sensor as rack03 chassis 02 S02 healthy. We can then go back to the input sensors. The first of the sensors is power. Here the sensor expression specifies top-down +1, which means that the sensor should be one level below the topmost level in the sensor tree. At this level, the only node that is hierarchically related to S02 is C02, so the chassis to which S02 belongs. So the sensor is resolved as rack03 chassis 02 power. We can then go on to the CPU cycles and cache misses sensors. The sensor expressions here are in the form bottom-up, which means that the sensors should be at the deepest level in the sensor tree, but additionally we also find a filter expression which drives the horizontal navigation. Here, only the nodes that match the CPU keyword should be taken into consideration. At the deepest level in the sensor tree, there are only two nodes that satisfy this requirement, and these are CPU 0 and CPU 1, so the CPUs that belong to the compute node S02. So we pick the CPU cycles and cache misses sensors from these two CPUs. It should be noted finally that in the bottom-up and top-down syntax, the root node of the sensor tree is not included. It can be seen how this kind of approach greatly simplifies the instantiation of ODA models at scale, since we can use very compact configurations that can then be resolved thousands of times arbitrarily. We now discuss a series of case studies that we carried out using Wintermute on our HPC systems. The case studies were chosen according to their notoriety in the literature, so as to show how Wintermute is applicable to them. They were carried out on the CoolMUC3 HPC system at LRZ. CoolMUC3 is a small-scale cluster with 148 compute nodes, each equipped with Intel Knights Landing CPUs and with warm water cooling. DCDB is deployed on this system for continuous monitoring. The first case study was carried out in-band with the aim of performing prediction of power consumption at the outlet in the CoolMUC3 compute nodes. To this end, we use our regressor plugin for Wintermute, which enables random forest-based online regression of arbitrary monitoring metrics. The plugin works as follows. At each computation interval, the regressor plugin fetches sensor data according to its block configuration and processes this data to produce feature vectors. The feature vectors are then accumulated in memory until a certain size for the training set is reached, at which point training of the random forest model is performed and regression can start. In this case, both the sampling and the regression are performed every 250 milliseconds. On the right, we show an excerpt of the time series for the original power consumption as well as the predicted power consumption. It can be seen that the predicted power consumption closely follows the original one, even though it cannot capture some high-frequency oscillations as well as power spikes. These are inherently noisy and unpredictable events for machine learning models. In the second plot, we show instead the bar plot of the average relative error values in function of the power bands, as well as the probability distribution function of the original power consumption. It can be seen that the PDF is very unbalanced, with one class of power values being extremely overrepresented compared to others. Despite this, the global average relative error of the model amounts to 6.2%, so a very positive result. Additionally, also the overhead impact on running HPC applications was found to be very low at around 0.1%. The second case study is specular to the first one and was performed instead completely out of band. Here we wish to characterize the performance of CoolMUC3 as a whole, dividing the compute nodes in classes. To this end, we use a clustering plugin for Wintermute, which performs Bayesian Gaussian mixture clustering. This will be clearer looking at the scatter plot on the right. Each point in the clustering space is a compute node in CoolMUC3, with its 2-week average power consumption, temperature, and CPU idle time. We apply clustering on this clustering space, where sampling is performed every 10 seconds, and clustering itself every hour. It can be seen that the outcome is fairly interesting. We have a main cluster which captures most of the compute nodes, which have very similar performance in CoolMUC3, and additionally also another 2 clusters which are much smaller but instead capture nodes that have either very low average power consumption or very high average power consumption. Finally, a series of nodes were identified as anomalies, outliers, because their performance deviates from the identified clusters significantly. It can be seen how this kind of approach is able to highlight anomalies in an HPC system as well as to characterize its performance as a whole. This can be especially useful to system administrators and also researchers. The last of our case studies pertains job level analysis, and is a mix of the previous two ones. In this case, we use a two-plugin pipeline. The first of the plugins, called Perfmetrics, computes a series of metrics within pushers at the CPU core level that describe performance, for example, cycles per instruction, memory bandwidth, flops, and so on. The second plugin instead is called Job Aggregator and operates out of band in a collect agent. The Job Aggregator plugin, as the name implies, performs job-level aggregation, and it captures all of the metrics computed by the Perfmetrics plugin. Specifically, for each job, the Job Aggregator only picks the data from the compute nodes on which the job was running and computes deciles for them, characterizing their distribution. In this case, both the sampling and the aggregation are performed every second. On the right, we can see the observed results for some of the applications that we tested. In particular, here we show a run of the LAMPS application from the Coral 2 benchmark suite on 32 CoolMUC3 compute nodes. Here we show the cycles per instruction. It can be seen that as soon as the application starts, the deciles of the CPI metric drop to a value of around 1, which indicates good performance and in general good usage of the compute node's resources. However, the same does not apply for other applications. If we consider, for example, the neckbone application, it can be seen that after the first part of the run, the CPI deciles deviate to very large values, indicating the presence of a performance bottleneck somewhere. This kind of approach is very effective at highlighting performance bottlenecks and in general the behavior of HPC codes and can be extremely useful to application developers. In this case, the impact on overhead was very low as well and below 0.5% against the 32 node application runs that we show here on the right. Wintermute makes it very easy to instantiate ODA models on HPC systems, even in production environments. And while optimal results could be obtained with specific plugins and training sets tailored to the specific use case, even general purpose plugins can lead to very positive results, as shown here. Additionally, configuring models in Wintermute is extremely simple. On the right, you can find an excerpt of the configuration for the regression use case that we have shown before. In light of this, we managed to deploy Wintermute and its job analysis pipeline on the Supercomputing system at LRZ. Supercomputing is the flagship system at the Leibniz Supercomputing Center. It is number 9 in the top 500 list as per November 2019, and it comprises 6,440 compute nodes. These are arranged over 8 different islands, each containing 792 nodes. We will now describe how Wintermute is deployed on this large-scale system. Starting from the compute nodes, here we find DCDB pushers running, collecting sensor metrics and processing these metrics via the Perfmetrics Wintermute plugin. The data is then sent out to collect agents running in management nodes within the same island. The data is sent out via the Ethernet interface in each compute node and not the standard Intel OmniPath one, so as not to interfere with running HPC applications. In the collect agent, we have a job aggregator plugin running. As discussed before, the job aggregator plugin performs aggregation at job level, and we distribute workload as follows. Each collect agent only treats the jobs that have the majority of their compute nodes within the same island as the collect agent. This has an additional side effect, which is optimized ODA performance, because most of the data that a collect agent will need will be already contained in the local sensor cache. However, for jobs spanning multiple islands, collect agents can simply query data from the remote Apache Cassandra database. In this case, we use a distributed Cassandra instance over 2 separate servers. The data can finally be visualized online or offline via either the Grafana DCDB dashboard or any other visualization framework. This deployment is still ongoing, and we will have more information for you soon. To conclude, Wintermute is a generic framework for enabling operational data analytics on HPC systems. It was designed after an extensive requirements analysis and can be integrated into any monitoring system. Our DCDB implementation is currently being deployed on the Supercomputing system. As future work, we plan to identify additional production use cases, improve the block system, as well as investigate high reliability features. Here you can find some contact information, and finally I would like to thank you for your attention.